Hello, everyone. Welcome back. So this is the fourth lecture of the Distinguished Lecture Series offered by Professor Rob Hyndman. My name is Tao Hong from University of North Carolina, Charlotte. I'll be your moderator for today. If you have any questions, you can type in the Q&A window or you type in the chat box. All right. Again, this is the last lecture of this four-lecture series. All right. So Rob, go ahead.
Thanks, Tao. You just move things around here. Okay. So as Tao has said, this is the last of these. And just to recap where we've come from, we started with talking about hierarchical time series and the concept of reconciliation, looked at different perspectives on that. And then earlier this week, we discussed probabilistic reconciliation. So what I want to do today is to add the time dimension to that process. So just a bit more on the recap. So the idea is you've got a lot of series that are related due to aggregation constraints or sometimes linear constraints. So for example, you might have a series that is the sum of other series and you want the forecasts for the total to add up to be equal to the sum of the forecast for the disaggregate series. So forecast reconciliation involves forecasting everything and then adjusting the forecasts in a second step to make sure those constraints are imposed. The optimal solution is MINT, minimum trace reconciliation, and it gives optimal point forecasts, but where MSE is the objective function, and it gives optimal probabilistic forecast if the forecast distributions are normal. And then last time I talked about if you don't want to assume normality, you can use a type of bootstrap to ensure you get coherent forecasts by reconciling sample paths. Okay, so, and in terms of notation, we have Y as the vector of all the series you're interested in, B is the vector of the most disaggregated series, and S is how those two things are connected, how you get from the bottom level series to all of the series. And I'm using Y hat for the base forecast, the original ones which don't add up. You forecast everything, but they won't necessarily be coherent. The reconciled forecasts are of this form where Y tilde is equal to S times a matrix G times Y hat. And that G, if you're using MINT reconciliation, is given by this expression here. So that's sort of the basic idea. So what I want to do first up is to talk about temporal reconciliation, where you, instead of trying to reconcile lots of different series with the same time frequency, what we're trying to do here is to forecast the same series, but at different time frequencies, and then reconcile those. So start with something really, really simple, which is quarterly data. So suppose you had quarterly data and you wanted to forecast that, but you also wanted to forecast the annual data, and then you wanted your quarterly forecast to add up to your annual forecasts. So the idea is you forecast all of the series, both the quarterly series and the annual series separately, and then you use the reconciliation ideas to combine them. And you can do that if you write the Y vector like this, where these are your quarterly series here that you've stacked up, you know, quarter one, quarter two, quarter three, and quarter four. And then your annual series is at the top, like that. So the thing in square brackets is how many of the most disaggregated series are combined to form that one. So these are ones because these are the quarterly observations, and this is your annual total. And so, of course, you get a row of ones to construct the annual total from the quarterly data. And the tau, the subscript tau, is being used as the index of the largest temporal aggregation level. So in this case, that's a year. So you're observing data at a quarterly level. And when you sum that up, we're observing it as at an annual level. So tau is the index of the annual level here. But I could also add up each of the quarters to form half years. So I get semi-annual data like that. And then I would just add in a couple of extra rows here, these ones, which would be the sum of the first two quarters and the sum of the last two quarters. And so the idea in temporal reconciliation is we put in all of the possible aggregations and then try to make sure that they are reconciled. Let's do something a little more complicated, which is monthly data. So at the monthly level, I've got 12 observations per year. So that's the bottom of this table here, down here. I could aggregate the monthly data to form quarters, and then the quarters, of course, to half years and the half years to years. But I could also aggregate it differently. I could sum 2 months at a time, and then each of those would form 4-month aggregations, and those would be added up to form annual aggregations. There's nothing magical about quarters as the sort of one of the intermediate levels. I could actually have thirds, which are what's going on here. So these are third years, and these are 1/6 years, and these are 1/12 years or months. Or I could do all of them, all of those different possible aggregations. Even though I can't write them in the same hierarchical tree, I can actually form all of those different aggregations. And that gives me this great big matrix of the summing matrix and all of these things. So that's the annual data, that's the half-yearly data, that's the 1/3 year data, that's the quarters, that's the 2-month data, and that's the monthly data there. And these are bold, means it's a vector because there's more than one observation in there. I can do all of that and get a big lot of different aggregations and a big summing matrix. And in general, once you see that idea, in general, you can write it down like this, that if you observe the original time series Y1 up to YT at frequency M, so M is like 12 if it's monthly data or 4 if it's quarterly data, then I can form lots of different temporal aggregations using this equation in the yellow box, and they will give me different ways of adding things up, where K is the number of observations, this K here is the number of observations that form that particular temporal aggregation. So K must be a factor of M. So remember, for monthly data, it was 1, 2, 3, 4, 6, or 12. For quarterly data, it was 2, 4, or 1. So K is the factors of M, and I just add up the various different possibilities. You get a single unique hierarchy when there's no co-prime pairs like you do for quarterly data, but not for monthly data. And the seasonal period of the aggregated series is M divided by K. So writing this out in our full notation, we have all of the different temporal aggregations for year tau. We have the summing matrix that I just described, and then we have the bottom level series, so that's at the most temporally disaggregated level. And then I can write down the S matrix using this, this over here, using Kronecker products to construct all of the different aggregations. So the circle with a cross through it is a Kronecker product. So that's what temporal reconciliation is. It basically takes your most disaggregated data, aggregates it all up into different temporal buckets, forecasts all of them independently, and then reconciles all of those forecasts. Now you might wonder, does that actually give me any benefit? Like I'm not adding any new data. I'm using the same data over and over again with different temporal aggregations. Turns out that you get better forecasts when you do that, and I'm going to demonstrate that using an example. I'm going to use the Thief package to show you this. The Thief package is an R package. Thief stands for Temporal Hierarchical Forecasting. And I'm just going to do a very simple monthly example. So this is accidental deaths in the US during the 1970s. So it's a series of 6 years of monthly data. And in the Thief package, I can just pass that object, that time series, to the Thief function. I can say use ARIMA models, and then the third argument here is how do I want to combine them? So I'm going to use the structural reconciliation approach. And it comes back with some forecasts. And that's it. So it's actually gone away and it's done all of the temporal reconciliations. It's forecast all of them using ARIMA models. It's reconciled them all, and it's given me back only the bottom level reconciled forecasts. Because if I want the others, I can construct them from them. Let me now do it in stages. So that's the really fast way to do it, but let me do it in stages to show you what's going on. So what it does is it forms the aggregates. So you don't have to do this in practice. I'm just going to show you, all of the steps that were involved in that single call. So the TS aggregates function creates all of the aggregates. So that's the monthly data, the data at frequency 6. So that's 2 monthly data, 3 monthly data or quarters, 4 monthly data, half-year data, and 1 year data. And then basically it's constructing forecasts from all of those using a REMA model. So it's applying the auto-AREMA function on each of those series, and it's forecasting 2 years ahead. And then it's applying this reconcile thief function to reconcile all of those forecasts, and it's giving me back only the monthly forecasts. So this set here is exactly the same as what you got back when you asked for reconciled forecasts using the thief function directly. What does that look like? Oh, there's the other one. So there's different levels of aggregation. You get all the different types of forecasts. What does that look like? Well, here is the data is in black, and my forecasts are in blue and red. The red are the unreconciled ones, the ones you get if you ignore all of the other temporal reconciliations. So you can see that for the monthly data, it's just picked up the pattern and pushed it forward. For the 2 monthly, so on. The annual data is the interesting one here. There's actually not that much data because there's only a few years, only 6 years. And so it's used a very simple model, and it's just taken basically the last observation. So it's using effectively a naive model for the next 2 years. But when I use more of the data, like when I use more observations over the same period, such as monthly data or 2 monthly data or quarterly data, the models are picking up a small trend at the end of the series here. And so those forecasts, the disaggregated forecasts, are trended, whereas the annual forecasts are not trended. But when I reconcile, of course, they all have to follow the same pattern. So when I reconcile, the annual forecasts become trended, these blue dots. So what's happening is it's learning some of the signal from the more disaggregated data, and it's applying it to the more aggregated data. And it's also happening the other way around. You don't see it here so much, but it's happening the other way around as well. Sometimes at the higher levels of aggregation, you get to see some signal that's being lost at the more disaggregated level because they're noisier. And so you get benefits at both ends. Okay, let me do some more examples. So I'm going to demonstrate that this actually does help by using all of the M3 monthly data. So we're just going to take all 1,428 series. We're going to forecast 18 months ahead, like that was what was required for the M3 competition. I'm going to use ETS and AREMA models, and I'm going to see how much our temporal reconciliation improves the results using just temporal reconciliation applied using those two models. I'm going to take some different types of reconciliation here. I'm going to try diagonal. I'm going to try diagonal with common variances, which sort of makes sense for this, because you would expect, for example, the February forecast to have the same variance as the March forecast, to have the same variance as the April forecast. So if they're on the same frequency level, they should have the same variances. And then what's called the structural approach, which is just assuming that everything at each level everything at the bottom level has the same variance, but they're all independent of each other, which is not true, but maybe is a decent approximation. Okay, so here are the results. And this is really quite astonishing how much better you get using this very simple approach. So this is across all 1,428 series. What I've got here is the original forecasts. So they're all ones because that's relative to that. And then I've got, if I just used bottom up at the annual level, if I used one of these 3 different types of reconciliation, so that's the annual level here, semi-annual down, and so on. So presumably we're interested in monthly forecasts with monthly data. So this is the number here that's telling us how big our improvement is. It's about 3 to 4% improvement by doing this temporal reconciliation. Not adding any more data. I'm using the same data over and over again, but fitting different models to it. And I'm getting 3 to 4% improvement in my monthly forecasts as a result by using relative mean absolute error. Mean absolute scaled error, it's about 5%. This is really quite amazing. That's free. That's free benefit just by extra computation. I haven't collected any more data. In the ARIMA case, it's similar, 3 to 4% in root mean squared at root mean absolute error, 3 to 4% in mean absolute squared error. And at the other levels of aggregation, it's much more. So if I actually wanted annual forecasts, I'm much better off doing this than taking the annual data and producing forecasts. If I just took the annual data and produced forecasts, I'm getting forecasts that are worse by about 33%, or 30% here, 25% here, 18 to 19% there. That's just taking the annual data and producing annual forecasts. If I use the monthly data and the bi-monthly data and the quarterly data, all the different temporal aggregations, and do this approach, my annual forecasts are improving by around 20 to 30%. So it's an extraordinary benefit just by a little bit of extra computation. Let's do another example, a little more complicated, because this is not monthly data now. I've got weekly data, and this is on accident and emergency services demand in the UK. So I've got data from November 2010 to June 2015, and I've got different types of aggregations here, different types of series, and I'm not going to worry about the cross-sectional aggregations here. I'm just worried about the temporal ones. So think about all of these different series, and we're interested in forecasting at different levels of aggregation, so weekly, or maybe monthly or annual. And that's important because for planning purposes, for running the organization, you need forecasts at different types of aggregation. You want certain types of forecasts if you're planning how many staff you need on the wards for the next week or few weeks. You need different aggregations if you're planning, do I need to build a new hospital in the next few years? So here is the results using a sort of holding back the last year of data. So I've got 4 years of annual data, and I'm just predicting the next 2 years. So holding back 2 years of data, predicting the next 2 years, years 5 and 6. That's the annual, and here is the weekly, and I've got bi-weekly where I'm just adding 2 weeks together, adding 4 weeks together, adding 13 weeks together, which is roughly quarterly, adding 26 weeks together, which is roughly semi-annual. And again, the blue is my reconciled forecast, the red is the actual. And you can see at weekly level, so red is the base, the original forecast. You can see at the weekly level, it's quite noisy. There's a lot of jumping around, and the model, when I fitted it to this noisy data, is this red series here, has not picked up any trend at all. It's fairly flat. Again, the noise has dominated, and it's made it difficult to detect some of the signal in the series. Whereas, say, at monthly level, it's much clearer that there's a trend, and that there's this seasonality that looks like this, and the models pick that up really well. The red dashed series here. By the time I get to annual level low, again, there's too few observations, and it hasn't even picked up what's pretty obviously a trend, simply because there's not enough data to estimate that effectively. And so my forecasts are just the mean here, which is a pretty bad forecast, obviously. But when I do the reconciliation, the fact that it's picking up a trend in these middle series here and here and here and here is being then shared across all the series through the reconciliation process, so that these are now forecast, and this is now trended, and that's now trended. Similarly, the seasonality which is being lost pretty much in this noisy weekly data, but is being picked up really well here and pretty well here, that's being applied across the board. And so you can see that the weekly forecasts are now much more seasonal than they after reconciliation than they were before reconciliation. So you get a lot of borrowing of strength from different temporal aggregations because the signal is amplified at different levels of aggregation. If I just took the last 52 weeks as a test set, fitted ARIMA models and looked at how well things did, at the annual level, my base forecast MASE is 3.4, the reconcile's 1.9. So I've got a 40 to 50% improvement at the annual level by looking at all of these things. At the weekly level down the bottom, I'm getting a 17% improvement, and in the middle, 19%, 16%, and if I'm averaging across all 52 weeks, about a 5% improvement, but always an improvement. So, temporal reconciliation is something that I think should be done much more frequently because it's pretty quick and easy to do, and you generally end up with better forecasts. Okay, let me now talk about cross-temporal. So that's where we've got cross-sectional reconciliation as well as temporal reconciliation. We're interested in forecasting lots of series, and we want to make sure that any aggregation constraints are retained, but we're also interested in using the temporal direction to improve our forecast by using different temporal aggregations and making sure they add up appropriately. So I'm going to take a really, really simple example because it gets a bit complicated when we try to think about both types of reconciliation at the same time. So in this example, I'm just going to use 3 different series. So this is my total, and this is my X series, and this is my Y series. So the total is equal to the X plus Y series. So again, this is a very simple example just so that I can write things down. In practice, we've usually got a lot more going on than this. But this time I've just got 3 series, X and Y, which add up to the total. And we've got quarterly data. So for each of these circles, I have got a setup like this where I've got quarterly data, half-yearly data, and annual data. And so for this box, I've got a setup like this, and similarly for this one, and similarly for this one. So I've got 1 aggregated cross-sectional series. I've got 2 bottom-level cross-sectional series. I've got 3 different types of temporal aggregation. It's quarterly series. Oops, that's a mistake. It should be a 4. Quarterly series, so M is equal to 4. Then I want my Y to be the series at the most temporally disaggregated level, the bold Y, including all of the cross-sectional disaggregations and all of the aggregations. Okay, so I want it to be at the, so Y sub T is the most temporally disaggregated, so that in this example it's quarterly, but I want to include all of the cross-sectionally disaggregated and aggregated series. So that's Y, and then for each element of that, I can expand it to include all of the temporally aggregated variants. Okay, so my bold-faced X sub I of tau is for the aggregated for all of the temporally aggregated variants from the K1, which is the most temporally disaggregated, KP is the most aggregated. And then I add them all up into a big vector. So I can write down for this problem the structural cross-sectional matrix. So for this little example, that's just going to consist of a 1, a 1, a 1, a 0, and a 0, and a 1. So that's the cross-sectional structural matrix. this guy. So I'm going to call that CS for cross-sectional and S for the structural matrix. I'm going to also have a temporal structural matrix. So that's going to, for this example, that's going to consist of an identity for the bottom 4. And then above that, I'm going to have a 1, 1, 0, 0, and then above that, I'm going to have a 0, 0, 1, 1, then a 1, 1, 0, 0 for these two series. And then at the very top, I'm going to have 1, 1, 1, 1 for this annual series. So that's going to be my matrix for the temporal structural matrix. This guy, I'm going to call that sub TE for temporal. And then the whole thing, when I put it all together, I can use a Kronecker product like that. So cross-sectional Kronecker product with temporal, and I will get this big matrix where, and then my series of everything, X sub tau, is going to be this new matrix times the bottom level series like that. So for this example, I can write it like this. So there's black means a 1 and a white means 0. So my structural, my cross-sectional structural matrix is this one. My temporal structural matrix is this one. I do the Kronecker product and I end up with this set of this matrix here. And that includes all of the different temporal and cross-sectional disaggregations. Okay, so you can see that if I had a big problem like weekly data or monthly data and hundreds or thousands of cross-sectional series, this is going to get enormous. But mathematically, everything will work just the same. Now, I did introduce the constraint matrix approach last week, and that can also be written in this form, and it will be a smaller matrix because the constraint matrix approach is a more efficient way of doing it. So if I write down my cross-sectional constraint matrix approach, my temporal constraint matrix approach, then I can form the cross-temporal constraint matrix using this thing here. Okay, so that's cross-temporal forecast reconciliation. I'm going to hold off on doing an example until I do the probabilistic version of it, because that's in many ways more interesting. So the probabilistic version, and I'm only going to talk about how to do it non-parametrically, because that's actually much simpler. Normally in statistics, the parametric versions of things are simpler. Not true here. It's actually simpler to do things non-parametrically. Now, you remember earlier in the week, I talked about bootstrapping for probabilistic forecast reconciliation. And we had to make sure when we did the bootstraps that we were grabbing errors at the same time for all series. So with vertical stripes in my graph. And the idea there was to preserve the cross-sectional correlations in our bootstrap samples. We didn't have to worry about temporal correlations because we were assuming the models were actually good models, so therefore they should be uncorrelated errors in the time direction, but they would still be correlated in the cross-sectional direction. Now it's a little more complicated because of all these temporal aggregations, and they're going to be related to each other. I mean, the annual error is going to be related to the quarterly errors, but they're going to be related to the monthly errors. So I have to be a little careful here. I want to simulate future sample paths from all of the models, like I did before, and then reconciling them. But I need to generate samples that preserve both the cross-sectional correlations and the temporal correlations. So what I'm going to do is to draw samples of the series from the same time, from the most temporally aggregated level, and then make sure that I keep the same time period for the others. It's much easier to see this in a diagram. So suppose suppose I've got quarterly data. It's always simpler to talk about quarterly data because I can write it down on a screen. Suppose I've got 4 years of quarterly data, and I've got my total, my X series and my Y series. So this is equal to, this one is equal to this one plus this one. These are my errors. And so I'm going to color the errors in year 1 green the errors in year 2 blue, the errors in year 3 red, and the errors in year 4 as this grey colour. So that's for the annual data. Semi-annual data, I'm going to have more errors because I've got more observations. So instead of having 4 time periods, I've got 8. So I'm going to colour them in the same way. And at the quarterly level, I'm going to have 16 observations, 4 years of quarterly data. I'm going to colour them in the same way. Okay, so this little diagram is the errors from fitting my models to these 4 years of quarterly data. When I come to do bootstrapping, I'm going to have to sample from these errors. So I'm going to sample in such a way that I always keep the same colours, because that always keeps the same years together. So I will grab a year of the annual data. So remember, in bootstrapping, I'm just resampling from the errors. So I'm resampling from here. So let's say I take a resample from that. I'll end up with different years appearing at different times just because of the sampling. So I might reorder it like this, and there I have to reorder all of the others in exactly the same way. The next time I might draw a different sample, and it might have 2 versions of the same year being drawn. So I've got the red year once, the blue years I've drawn twice, and the green year I've drawn once, and I haven't drawn the 4th year at all. I just have to preserve the same structure everywhere else. So I'm preserving both the vertical structure this way, like I did before, but I'm also preserving the same year here, here, and here to make sure my temporal correlations stay the same, are preserved, sorry. Okay, so cross-sectional is being preserved by taking vertical stripes. Temporal is being preserved by making sure my years are the same years every time I draw a bootstrap sample for different temporal aggregations. And then it should work. One problem here, of course, is that because I'm having to sample whole years, and if I have a small set of data, I don't usually have a lot of samples to draw from. And in this little example, I've only got 4 years, so I can only draw from 4 different time periods. I can improve things a little bit by starting the year in any quarter. The year doesn't have to start in quarter 1. It can start in quarter 2 or quarter 3 or quarter 4, and I can draw samples that way. So I can increase the number of samples I can draw by starting in different years, provided I keep the same time periods in all of my aggregations. So let's do some examples. I'm going to take that idea of the cross-sectional and the temporal and the probabilistic stuff, and I'm going to do a couple of examples. So the first one is quarterly Australian GDP. So GDP can be constructed in a number of different ways. You can construct GDP through income, and then you form a particular tree, and the different sources of income should add up to GDP. You can also construct it using expenditure, and so different expenditures should also add up to GDP. It's too big to put on the same diagram, so some of these cells, this one, for example, I can split into further disaggregations, and this one here, I can split into even more disaggregations. So these are big trees of data, but they should add up to give me the same GDP. When you're doing reconciliation, forecast reconciliation for GDP, you're going to make sure that your forecast, the income, adds up to the same forecast as your forecast of all the expenditure components. So I'm going to take quarterly data from 1984 to 2018 for Australia. There's 95 series once I do the GDP and all of its disaggregations on the income side and all of its disaggregations on the expenditure side. I'm going to use a time series cross-validation approach where I take a training set, and then I'm going to increase and take a training set and forecast up to 4 steps ahead. And then I'm going to increase my training set by 1 quarter, forecast 4 steps ahead, increase it again, forecast 4 steps ahead, and so on. I'm going to use ARIMA to do this with an automatic ARIMA modeling process for each of the forecasts at quarterly level, at half-yearly level, and at annual level. And there's different ways I can do the reconciliation, different ways of choosing the covariance matrix. And I'm not going to go through the different ways. I'll give you the reference to the paper that talks about where you can get these different ways of doing calculating the covariance matrix, but there'll be cross-temporal bottom-up, which basically is ignoring the correlations between, it's not trying to estimate the covariances between bottom level and higher level, or it might be partly bottom-up, where you're trying to estimate the covariances at the temporal side, but not on the cross-sectional side. There's one variation where we allow some overlapping in the residuals when we estimate the covariance. And this one is block diagonal shrinkage. This one is weighted least squares, so ignoring the off diagonals with estimating the variances. Yeah, there's lots of ways of doing this, and we tried a whole bunch, more than what I'm going to show you. Because these covariance matrices are enormous, and they're highly structured, and they're hard to estimate. So we thought, let's try a bunch of different ways of doing it and see what works. So here is the results, and I'm showing here CRPS skill scores. So CRPS, remember, is continuous rank probability score. It's a measure of accuracy of a probabilistic forecast of the whole distribution. It's a skill score because I'm comparing it with the original forecast, the base forecasts. So it's a number that if it's lower than 1, I'm doing better than my base forecasts. And if it's bigger than 1, I'm doing worse. The base forecasts, of course, are not coherent, so I don't really want those ones. But I'm trying to find some coherent forecasts that are better than that. And you can see that some of these methods of estimating the covariance matrix have ended up with worse forecasts. So they're introducing error because it's a hard matrix to estimate, but some of them have done pretty well. And this one, which is optimal cross-temporal reconciliation using just weighted least squares variances, so just ignoring the off diagonals, has given me pretty good forecasts at the at the quarterly level. It's about a 2% improvement. At the annual level, it's about a 14% improvement in my accuracy by doing this reconciliation. I can check whether those improvements are significant, and in fact, they mostly are. So this is using the Nemini test. The confidence intervals are shown using the bars, 95% intervals. The blue ones are not significantly different from the best, and the red ones are significantly different from the best. The base forecast is shown with a triangle. So that's one that's sort of a reference. I don't want that forecast because they're not coherent, but it gives me, and it shows me how well, whether my reconciliation is doing better than that. So we can see that this bottom method is actually doing really well. And it's significantly better than the original forecast and significantly better than many of the other alternatives. I'm showing mean ranks here, and the significance differences is shown if you've got non-overlapping intervals. Okay, let's do a different example. So this one, we'll go back to what I started with in this whole series, which is the monthly Australian tourism demand. And we had Australia split into zones and into states and zones and regions. And we also have it split by purpose of travel. So I have a hierarchical structure in the geography, states, then split into zones, then split into regions. And I have a grouping term, purpose of travel, which is crossed with all of those other terms. Purpose of travel has 4 levels: holiday, visiting friends and relatives, business, or other. Australia is unusual geographically because some regions are enormous, like this region here, and other regions are so small you can't see them, such as around Melbourne and around Sydney. That's simply because of the distribution of population. Population is heavily centred in certain urban areas, and most of the country out here, this is all desert, and basically no one lives there. And so for tourism, parts of the country very few tourists go to. Okay, so that's the cross-sectional hierarchy, the cross-sectional grouping, and I've got 525 series like this. And then in the temporal direction, I've got monthly data, bi-monthly, quarterly, 4-monthly, semi-annual, and annual. I've got all those different frequencies. So my monthly data is going to go from January 98 to December 2016. I'm going to use time series cross-validation again, where I take in a training set, and I'm going to slowly increase the size of that. My training set is 10 years, and then I'm going to increase it 1 month at a time. And for each training set, I'm going to produce forecasts for the next year. So this is all of my factors of the period 12, and this is how far ahead I'm forecasting. So for 2 monthly data, I'm forecasting 6 periods ahead, because that gives me a year. For 3 groups of 3, which is quarterly data, I'm forecasting 4 steps ahead, which gives me a year, and so on. And the monthly data, the annual data, I'm going to forecast 1 step ahead, because that's a year. And this time I'm going to use ETS on the log transform data, because there's some heteroscedasticity that I need to worry about. I also wanted it to be positive. We don't want negative tourists, so that's why the log was being taken. Similar set of reconciliation approaches. I'm just again showing a subset of all the ones we tried, some of which worked well and some of which didn't. Like that, and here are the results. So again, the base is my original forecasts, which are not coherent, so I don't want to use them, but they give me the sort of something to compare against. And then I'm doing CRPS skill scores again. So a number less than 1 is better than that, and a number bigger than 1 is worse than the base. So the red ones are not interesting. That's where my reconciliations actually made things worse. And I can see that this is optimal cross-temporal reconciliation with block diagonal shrinkage. And this one is optimal cross-temporal reconciliation with H-step shrinkage. So just different ways of getting the covariance matrix. And you can see that it's improved things. So for the monthly data themselves, I'm getting an improvement of about 5% with the best method. But with almost all of the methods, I'm getting an improvement of between 2 and 5% by doing this, by doing all of the different reconciliations. And so this is comparing with base, so comparing against what if I didn't do any reconciliation at all, if I just took the monthly data and forecast them as they were. Again, we can see whether those things are significant. Again, showing mean ranks, and the intervals, if they overlap, are not significantly different from each other. And you can see that these methods are doing significantly better than the base method by some distance. Okay, so the story there is, although computationally it can look a bit complicated, it does improve your forecast accuracy, and you are able to get coherent forecasts that will improve your accuracy, but also help with decision making, because you will get things that are coherent across different temporal levels and across different cross-sectional levels. Let me finish by just talking a little bit about software. So far there's a bunch of R packages and a bunch of Python packages that are available. I'll just talk briefly about what each of these are. So HDS was the very first one that that I first wrote, and then a bunch of other people joined me, and that's sort of the original, and it only ever has done cross-sectional point forecast reconciliation, not probabilistic. But it's fast and it's scalable. I have reconciled 2 million series in 20 seconds on an old laptop. So it's using that package. So it's very fast, very efficiently written, but somewhat limited in that it only does the cross-sectional point forecast reconciliation. IIF was the one that introduced the temporal hierarchical forecasting. Again, though, it's only point forecast reconciliation, but it's pretty quick, and that's the one I demonstrated earlier in this lecture. Fable is a package currently in development, which we eventually hope will do all of this. It's much simpler interface than HDS, which is a little complicated. HDS is a little complicated to specify all of the aggregations you're interested in. Fable's really simple interface, which is nice. At the moment, it does cross-sectional point forecast reconciliation and probabilistic cross-sectional reconciliation. It doesn't do anything temporal or cross-temporal yet, but we are planning that it will. So that's being developed by my group at Monash. The main developer is Mitchell O'Hara-Wild. And it's part of his PhD project. So I'm hopeful in the next couple of years it'll be at a state which will be much have a lot more facilities and be faster than what it currently is. Foreco is a package developed by Daniele Girolamo from the University of Padua as part of his PhD project. It's the only package at the moment that does everything, cross-sectional, temporal, cross-temporal, and probabilistic. And it's under active development still. He's nearly finished his PhD, but he has plans to extend Foreco, and I'm working with him on that. Or planning to, haven't done anything on it yet. And the user interface at the moment is a little, tricky, but it does do everything and it's pretty efficient. And then there's a couple of Python packages. PyHTS is a package from Bohan Zhang from Beihang University in China, and it's available from his GitHub repo. And this one, hierarchical forecast. Oh, before I say anything, PyHTS, the one from Bohan, only does point forecasting, but it does cross-sectional and temporal. Hierarchical forecast is from Nixler, which Nixler has been producing some really high-quality Python software in the last year or so. And if you're working in Python, I strongly recommend their packages. Their current package does cross-sectional, but it does do it probabilistically as well, but not temporal. So there you go. So that's sort of the main software that's currently available. These two are under active development, and I think Nixler is still working on hierarchical forecast and is probably going to add more facilities to that. And I'm not sure about PyHTS, what Bohan's doing. I wanted to point out that there's a special issue on this topic coming in the IGF next year on innovations in hierarchical forecasting, and it includes a review article by a few of us, George Athanasopoulos, me, Nikos Kourentzis, and Anastasios Panagiotoulis. And this series of talks has been based on that review article. Obviously, in an article, we can say a lot more. And so if you're interested in the topic, I would suggest that's a good place to look. We've tried to cover all of the literature in the area. There is a preprint of that paper available. I put the link on this URL. This, of course, is the work that I've talked about over this series of lectures is due to a lot of people. And I just wanted to point out the most important people that have worked on this, which are shown on the screen. So the PhD student that we first worked on with this is Roman Ahmed, shown at the top left. George, of course, who's co-author of many of the important papers in the area. Hanlin Shang, who was the last author on the methodology paper. I'm not going to go through all of them, but let me just point out a couple of others. Shanika Wickramasuriya, who was the main author of the MINT paper, Anastasius Panagiotellus, who's been instrumental in the geometric approach to the problem and the definition of coherency with the problem. And down in the bottom right, Daniela Girolamo and Tommy D'Afonso, who've also made, they're from the University of Padova, have also made really important contributions, including the 4Echo software. And everyone else here I've co-authored papers with on this topic. If you want more information, the URL for this series of talks, including papers and links to papers, links to software, links to the review paper, and the slides are all at the top URL there. That's my homepage, my social media handles, GitHub handle, and my email address. And I just wanted to mention the papers that I've used in this particular talk. The temporal hierarchical paper, the first one was this one at the top in eJAW. The first paper that did cross-sectional, that showed how to do cross-temporal reconciliation is this one by Tommy and Daniela. And then the last paper, which does cross-temporal and probabilistic, which in a sense sort of completes the theory, is this one here by combining Daniela and Tommy and me and George. And we'll stop there. Thank you. Time for some questions.
Thank you, Rob. Yeah, I think there's one question in the Q&A so far.
Yeah, so in reconciliation, how do we deal with a collection with entry and exit or birth and death of individual series? Yeah, that's a really good question. In a lot of situations, you have series that begin partway through the data collection or might end. And some examples would be if you're forecasting products, sales of products. You might have a new product that comes in and you're interested in the total sales, and that product didn't exist at the start of the series and it comes along, and then a product might disappear. So yeah, that is tricky. The way I've dealt with it in the past is to basically have the series as zeros when the product is either doesn't yet exist, or zeros when it stops existing, so that you can still get your aggregations working properly. When you come to forecast that individual series, though, you need to basically ignore the zeros before the start, so treat them as missing, and then you can forecast that series. If the series has died so that it's actually become zeros and will stay zero forever, well, that's easy. You just set the forecast of that series to zero forever. So there's a little bit of fiddliness to think about, are the zeros real or are they because the product is dead? And then constraining the forecast of that series to stay zero. So you might make your base forecast zero. When you do the reconciliation, they're no longer zero. So that's a problem. So you then need to constrain them. So you can constrain them in one of two ways. You can use the immutable idea that I talked about in lecture 2, or you could just reset the forecast to zero after the reconciliation and then re-aggregate, which is called the set negative to zero problem. In this case, you're setting anything to zero for that particular series. So yeah, it's a problem, but you can deal with it. You just have to sort of think and be a little bit careful about how you deal with it. So Jerome's asking that in the first lecture, you showed us from your applied soft computing paper that non-linear reconciliation techniques perform really well compared to the theoretically sound linear techniques, but I didn't come back to it. What is your view? So that's the only paper that I've actually tried it on, Jerome. And in theory, you would think that should be able to be extended to cross-temporal, probably also to probabilistic if you use the bootstrapping idea, because you can apply the same mapping to the bootstrap samples, but I've just not done it. So yeah, it's an area for future research. Take that same idea and apply it in different contexts and see how it works. And also, I think the idea could probably be improved. We were using a couple of different machine learning methods to learn the mapping. One was random forest, I think, and one was XGBoost. I'm sure that you could do better than those two, but I'll leave that for other people to work on. Sarah is asking for temporal reconciliation where the base forecasts are recursive, such as for multi-step forecasts such as ARIMA. Have you looked into iterating the reconciled base forecast with the base models? That is, for example, reconcile the monthly forecast, put the adjusted month into the ARIMA, get new recursive forecasts, re-reconcile, and so on. I haven't thought about doing that at all, Sarah. That's an interesting idea. So I guess the advantage would be that you would get improved forecasts in the recursive process, and that might give you better forecasts overall. I doubt that it's going to make a lot of difference. But, you know, it might, but it does take a lot more computation. Interesting idea to try. I haven't thought about it. My gut feeling is that it's probably not going to make a huge difference, but you know, I could be wrong. Any other questions or comments?
Yeah, hey Rob, I just want to make a comment. You did reconciliation for I think M3 competition time series, 12,000 some. I've been working on electricity load for a long time, and I just want to confirm that in the electricity industry, power industry, if we were working on hourly data for long-term forecasting, do the reconciliation, we're getting much better results than doing the monthly forecast or even annual forecast directly. So that's also the same observation from a different business sector.
I'm not surprised because once you get down to hourly level, things can get a bit noisy, and generally you get improvements with these techniques when you're disaggregating, when you need to disaggregate a lot, because you're interested in hourly forecasts, for example. So you've got this highly disaggregated data, but the signal is more easily seen at higher levels of aggregation. So I'm not surprised, and it's good to hear that confirmed, because I have not tried it on the electricity problem.
Right, it looked like there are no other questions. I just want to thank you again, Rob, for these 4 amazing lectures. They will be archived and available for the members to view. Again, thank you so much, Rob.
Been my pleasure. Thank you.
Yeah. And thank everyone for coming. So if you have any ideas about distinguished lectures, topics, feel free to let me know. So we are reaching out to these prolific researchers and practitioners. We'll bring this back to the members. All right. Thank you, guys.